everybody. Welcome to the Morrison Planetarium. My name is Cheryl, and I have the pleasure of being your pilot today through a tour of the universe. And I'm not just the bodiless voice coming out of the walls. I am a real person, and I am right behind you in the control booth. Hello, nice to see some faces. Welcome. So this show is a little bit different than the ones we have throughout the day because this show is 100% live. I will fly us away from our home on Earth to explore our solar system, our galaxy, and go out to the visible reaches of the universe. Now, our spacecraft today is a software called OpenSpace that was built in partnership with NASA and uses models to create a 3D visual of the universe. It also uses updated information, so everything that we see on this tour is almost in real time out there in space. And finally, the software is also open source, so you can download it for free onto your gaming computers at home and explore the universe at your leisure. Before we start this tour, though, I do have some housekeeping items to review, so we all start off here on the same page. So first, just a reminder to please keep a mask on over your mouth and nose the entire time you are in the planetarium. And in an effort to keep the space clean for you and future guests, we don't allow any eating or drinking in here. If you have any electronics with you today, please take a moment to either turn those off or set them to silent. It gets pretty dark in here during the show, so any light or sound can be distracting to you or the folks sitting around you, and we don't allow any recording or photography during the show. Now, like I said, it gets pretty dark in here, so if you're standing or moving around during the show, it can be easy to stumble or trip. So for your safety, I ask that you stay seated for the whole show, but if you need to leave early, the exits are at the top of the planetarium up the stairs. And finally, the show gets pretty immersive. So if you start to feel any discomfort like motion sensitivity or dizziness, I suggest you close your eyes, take a few deep breaths, and that should give your brain a chance to remember you are comfortably sitting in a planetarium and not actually hurtling through space. All right, that's all for that. So let's get started on this tour. All right, so we are going to begin our journey a few hundred miles above the Earth here at the International Space Station, or the ISS. Now, this is essentially a large orbiting research station that slowly gets larger as more modules are added to the structure every year. It is the largest object that we have built in space so far, comparable in size to an American football field. And also lengthwise, it's about the size of our Academy building we're in today. Nations around the world participating in the ISS program send astronauts to live on the ISS, where they work through experiments to learn how things like water, fire, plants, and even how our human bodies function under the harsh conditions of space. And nowadays, the ISS is the farthest that humans travel into space. And at any one time, 6 astronauts can live on the ISS comfortably. Now, the ISS orbits the Earth 16 times every day, so it's moving pretty fast above us. And you can actually find out when the ISS passes over your area by checking online at spotthestation.nasa.gov. On a clear night sky, it'll look kind of like a bright little star that's quickly moving across the sky in a pretty straight line. Now, as we get farther and farther away from the ISS and our planet here, we're going to see how far our human influence has spread throughout space, how far humans have physically traveled, how far our spacecrafts have gone, and how far our human communications have gone as well. Now, next, we are going to stop by Earth's moon, the 5th largest moon in the entire solar system, which is pretty impressive since there are over 200 in our solar system. So let's mosey on over to our one and only moon. Now, our moon is Earth's closest natural neighbor. And for millennia, our moon has been important to humans, helping us track time and inspiring myths and legends of different cultures. Now, every 27.3 days, or about a month, the moon completes a full orbit around us. But we only ever see one side of the moon because it revolves around us and rotates on its axis at the same rate. Now, I've flown in a little bit closer here so we can see the many impact craters on the moon's surface. Many of these craters are named after different scientists and astronomers like Tycho, Marie Curie, and Tereshkova. And it may look like the moon's actually been hit by asteroids and meteorites more often than us. But Earth is a much bigger target, and we've had our fair share of impacts. But because the moon doesn't have an atmosphere like Earth, nor does it have any wind, water, erosion, or even tectonic plates, there is nothing to erase these craters after they appear on the moon. And most of these craters are very, very old. One of the more recent craters was formed over 100 million years ago. Now, the moon is as far as humans have ever traveled out into space. NASA astronauts Buzz Aldrin and Neil Armstrong were the first humans to walk on the moon's surface in 1969, and since then, 10 other NASA astronauts have walked on its surface. Currently, though, NASA is planning a new mission to the moon called Artemis, where they will send the first woman to the moon and lay the foundation for humans to plan missions to Mars. Now, our moon may be our closest natural neighbor, like I said. It only takes about 3 days to fly there, but it's still a whopping 250,000 miles away from us. And as we continue on this tour, distances are going to hike up into the millions, billions, and even trillions. And at that point, it doesn't really make sense to use miles or kilometers as a measurement of distance anymore. So instead, we're going to talk about distance using the speed of light. The visible light that we see is part of the electromagnetic spectrum, and it is the fastest thing in our universe that we know of, clocking in at almost 200,000 miles per second. So if NASA astronauts are traveling to the moon at light speed, instead of taking 3 days to get there, it would only take them 1.5 seconds. So we say the moon is about 1.5 light seconds away from our planet. Now, light speed is also a measurement of time, but let's talk more about that at our next stop, the sun. Now, our sun is 8.5 light minutes away from the Earth, and that means when we look at the sun from Earth, we are seeing what it looked like 8.5 minutes in the past, because it took 8.5 minutes for that light to leave the sun, move through space, and reach us on Earth. Now, our sun here is a middle-aged dwarf star, about 4.5 billion years old. It's mainly composed of hydrogen and helium, and its massive gravity holds our entire solar system together. And just like the Earth, the sun also spins on an axis. But because it's not solid, the sun is made of gas. Different sections spin at different speeds. The sun spins faster at its equator and slower at the poles. And obviously, we don't send humans to the sun, but in 2018, NASA launched the Parker Solar Probe to learn about our sun from up close. Recently, Parker Solar Probe entered the sun's solar atmosphere, closer than any spacecraft has come to our sun, where it sampled particles and the magnetic field there. So spending time learning about our sun can help us better understand our own Earth and other stars in our universe. All right, so now you can go ahead and stow away your sunglasses. We're going to head out to the other planets in our solar system. And as we move away farther here from the sun, I'm going to pull up their orbits so you can get a sense of where they sit out here in space. There we go. Now, first, we're going to see the rocky inner planets. We have Mercury, Venus, Earth, of course, and Mars. And then as we move farther out, we're going to see the orbits of our gas giants, Jupiter and Saturn. And at the very edges of our solar system, we have the orbits of our icy giants, Uranus and Neptune. Now, you may have noticed here that there's a pretty sizable gap between Mars and Jupiter's orbits. But this isn't just empty space, though. This is actually where we find most of the asteroids in our solar system. The main asteroid belt lives here. And in 2015, NASA used the spacecraft Dawn to explore a particularly unique body within this crowded asteroid belt, a dwarf planet named Ceres. So here is that dwarf planet's orbit around our sun. And not a lot of people have heard of Ceres, but there is another dwarf planet in our solar system that is very popular. Does anyone know the name of that other dwarf planet? You can shout it out if you know it. If you were thinking Pluto, you are correct. So Pluto, the dwarf planet out past Neptune, I'm going to pull up its orbit as we get farther out here. Now, the reason I bring up Ceres and Pluto is because they have pretty similar stories to each other in a way. When we first found Ceres over 300 years ago, we thought it was the only thing orbiting in between Mars and Jupiter. But around that same time, a lot of astronomers were starting to find a lot of small rocky objects that they were calling asteroids. So Ceres was changed from a planet to an asteroid. And similarly, when we first found Pluto, we thought it was the only object orbiting out here. But then, in the late 90s and early 2000s, astronomers started to find all these other objects. They found the Kuiper Belt. And so these are mostly small icy objects, but some of which are around the size of Pluto. And at least one is almost as big as Pluto. So instead of adding another dozen or so planets for all of us to memorize in school, astronomers around the world got together and created a better category for these small objects. They called them dwarf planets. And so now there are 3 requirements for anything to be a planet in our universe. 1, it needs to orbit a star. 2, it needs to be large enough or massive enough that its own self-gravity can pull it into a round spherical shape. And 3, it needs to have cleared its orbit. Well, I don't know about y'all, but I kind of lost Pluto in this Kuiper Belt. And so as we can see, it goes right through that Kuiper Belt and doesn't have a clean orbit. So as of 2006, we don't call Pluto a planet anymore, but it does still orbit the sun and is big enough to be a sphere. So it's a dwarf planet, shifting from the smallest of the planets to now the largest dwarf planet in our solar system. I call that an upgrade. Now, while we're out here and we can still see Pluto, let's use its orbit to get a sense of distance real quick. At light speed, to get from one side of Pluto's orbit to the other would take us about 10 hours. So that is 10 light hours across. Now we know that humans haven't traveled to any of the other planets in our solar system, but we have sent robots like rovers, probes, and other unmanned spacecraft to explore for us. So these orange lines here are showing how far our fastest and farthest spacecraft have gone so far. They're all traveling fast enough to escape the sun's gravity and leave the solar system. We have Voyager 1 and 2 and Pioneer 10 and 11, all of which were launched in the 1970s. And most recently, the New Horizons spacecraft, which went out to Pluto in 2015. And if you look carefully, you can see that short line there where it intersects Pluto's orbit. That is the New Horizons spacecraft trajectory. Now, they have all traveled fast and journeyed far, but even still, these spacecraft have only gone as far as light can travel in a single day. So that tells me that we have a lot farther to go here on our journey to get to the edges of the universe. So let's keep flying. We're going to fly away from our solar system and go out into interstellar space now so I can show you the very farthest our human technology has reached in the universe. Now this is the radiosphere. It represents how far radio waves emitted from Earth's radio and TV signals have traveled since we first broadcast them. Radio signals that were strong enough to escape our planet were first sent out in the 1930s, so this radiosphere is about 90 light years away from us in all directions. And radio waves travel at the speed of light, so this radiosphere actually gets 1 light year wider every year. And while we are out here, I also want to show you the other planets that astronomers have identified. So every single one of these markers is a star with at least 1 exoplanet around it. And that's a planet that's outside of our solar system. And now we have found thousands of weird and interesting exoplanets so far. We just surpassed 5,000 discovered exoplanets recently. And astronomers use telescopes like the James Webb Space Telescope to explore these exoplanets using infrared technology. Now, if you look carefully, actually, you can see that there are several exoplanets inside the radiosphere. So if there is any life on those exoplanets, they would be able to detect our old radio signals and TV broadcasts, which would be pretty amazing. But you know what? Let's keep going, because we are still just flying past stars in our galaxy. We haven't even gone outside the Milky Way yet. But as we zoom out here, I do want you to keep an eye on the radiosphere and see how long you can keep track of it. Soon, we're going to start to see the large-scale structure of our galaxy. We live in a spiral galaxy, so it's pretty flat like a disk, and it has spiral arms of gas, dust, and stars in it, and we are in one of those spiral arms, the Orion arm, about 2/3 out from the center. And right in the center, you'll see a bright group of stars that are densely clustered together. If you could see past all those stars, right to the very center of the Milky Way, you would see, well, basically nothing, because we have a supermassive black hole at the center of our galaxy. It's called Sagittarius A star, and it's about 4 million times the mass of our sun. All right, I'm going to stop flying for a second, give you a chance to spot the radiosphere. I can still see it pretty easily right there. So that tiny, tiny dot right there is the farthest that any of our human communications have gone out into space so far. And now we're up to distances of thousands of light years, because from one side of the disk to the other, our galaxy is actually about 100,000 light years across. But of course, our galaxy, with its roughly 400 billion stars, is just one galaxy out here in the universe. Every dot that we are seeing now is not a star, but another galaxy with its own billions or sometimes trillions of stars. Now, the closest large galaxy to our Milky Way is the Andromeda Galaxy, 2 million light years away from us. But don't worry, it's slowly moving closer each day. And it'll get here in about 5 billion years or so. Now, as you see here, galaxies are not evenly spaced out. They tend to cluster. The Milky Way and Andromeda galaxies are grouped with about 40 other galaxies in a cluster called the local group. And astronomers use the different colors we're seeing here to show the different galaxy clusters. Now, if we start to fly far enough here, we're going to see a strange shape that these galaxies seem to form. It's going to look kind of like an hourglass or maybe even a butterfly. I'm going to start to see it here soon. Now, the universe is not actually shaped like a butterfly, though I think that'd be pretty cool. But the universe, it looks like this because we're looking out at the universe from our perspective here on Earth. So this is a map of the galaxies that we can see and have found so far. And since this is from our perspective, it makes a few things look a little bit strange. For one thing, it makes it look like the Milky Way is right at the center of everything here. But as far as we know, there is no center to our universe. If you were to go to any of these other galaxies, it would also look like you're right at the center with everything else moving away from you. And the other strange thing is this pretty big gap we have up here and this pretty big gap we have down here. Now, these gaps exist here because the flat disk of our galaxy, which has a lot of gas and dust and stars in it, that flat disk obstructs some of our view of the universe around us. So there are even more galaxies to see and map in those directions. And over time, as we innovate our technology, we'll begin to fill in those gaps. Now, if we go a little bit farther here, we're going to start to see some of the earliest objects in our universe. They're going to come up here as red points of light. I'm going to go a little bit farther. Here we go. We're starting to see some of them. So these red points here, they are quasars, highly luminous cores of some of the first galaxies formed in the universe. Now, one of the largest known quasars is Ponua Aina, a colossal object powered by a supermassive black hole that's 1.5 billion times the mass of our sun. Now, this ancient quasar formed over 13 billion years ago, and when we use our telescopes to view these quasars or anything out in space, we're kind of time traveling. Because the light from these objects has to travel so far across space that by the time that light travels all that distance and gets into our telescopes, we're seeing the light of these objects as they were in the past, not how they look today. So this is the same point I made earlier about our sun. When we look at our sun, we're seeing what it looked like 8.5 minutes in the past because it takes that long for the light to reach us. So here, we're seeing the universe as it was about 10 billion years ago. And interestingly, that means we only have a little bit farther to go because there's actually an edge to everything that we can see in the universe. And that edge is all around us now. The cosmic microwave background radiation, or the CMB. Now, this light is the residual radiation from the Big Bang and is the earliest light that we can see with our telescopes. With a radio telescope that could see in the microwave range of the electromagnetic light spectrum, we could see this everywhere we look in the sky. In fact, the first radio astronomers were pretty confused by this. They looked up into the sky with their telescopes and thought they were getting interference everywhere they looked. But soon they realized that this was actually something out in space that they were actually seeing. And what we're seeing here is a few 100,000 years after the Big Bang would have happened. So you can think of this as a baby picture of our universe. It is the first light that we can see. But since this is the edge of everything we can see, that does mean we can't go any farther. So we've reached the end of our journey today, and we are going to begin our descent back home to Earth. Now, if we were actually this far away in space and we were actually flying at the speed of light, getting back home to Earth would take about 13.7 billion years. But thankfully, we're in a planetarium, so it should just take about a minute. Now, there's one more thing I want to point out as we zoom back home. All of this that we've looked at today, all of these stars and galaxies and the cosmic microwave background, that's not even everything that's in our universe. There's dark energy, a mysterious force that's causing space itself to accelerate as it expands. There's dark matter, a mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and at the edge of galaxies especially. And we call these things dark energy and dark matter because we're not quite sure what they are yet, but we do know that they make up about 96% of our universe. So everything that we've seen so far in this tour, that's only about 4% of everything that is out there. And sometimes knowing this makes me feel kind of tiny because we're this one little dot in a humongous universe. But then I remember that even as a small dot, look at all that we have found so far, almost entirely just by looking through telescopes. So there's a whole lot more to discover and a whole lot more to learn about. And that's what makes this such a wonderful time in human history. We're able not just to learn these things, but to share them like this, mapping the cosmos in 3 dimensions. We're finally starting to unravel the true nature of the universe, but we're still only starting to unravel it. And the rest, well, that's going to be up to the next generation of scientists back on Earth. And here we are, approaching that 3rd planet from the sun now. The only place in all of this, by the way, where we have found life so far, which is pretty incredible to think about after everything we have just seen. Our tiny blue and green home is a pretty special place in the universe after all. So I will drop you all off here. And that concludes our journey together today. So thank you so much for joining me on this tour through the universe.